Notice what are the brief synopsis of alcohols here. First, preparation reactions. Alkanes, there is only one reaction, that is tert-butane when you react with KMNO4 with OH minus, right? Usually not H plus, but usually mainly OH minus. That will give you tertiary butanol. Second, methane plus half O2 in the presence of copper and heat, that will give you methanol. So these two are the only alkane reactions that you need to remember, which will give alcohols. Alkenes, we can do hydrolysis. Pi bonds, when you react with H plus, they'll first form carbocations. Thereafter, water will attack, right? And as water attacks, you will get this OH2 plus, and OH2 plus will try to gain the electrons. Oxygen will gain the electrons, remove H plus away. So there are mainly four steps happening here. The first step is called protonation or also electrophilic addition. Okay.
Yeah.
And electrophilic addition is always the rate determining step. Okay. So this is the rate determining step. And you need to always check out the stable carbocation. So first one is stable carbocation. And once you get a carbocation, it can undergo rearrangement also. Here rearrangement is not there. So that's why I have not written. But otherwise the second step is rearrangement. Thereafter, the third step is called hydration because you are adding water. Afterwards, H plus is removed. So this is deprotonation. Clear? So you can see these are the main steps: carbocation, rearrangement, Markovnikov, and protonation and deprotonation. Clear? These are main pointers that you need to remember. Clear, beta?
Yes, sir.
Okay. See one example. D3O plus first carbocation is formed following Markovnikov's rule. Thereafter, 1,2 hydrate shift rearrangement. Then D2O, you will get OD. Similarly, if you have a pi bond here, H plus addition on this position, carbocation will come in this position. Why this position? Because the next step can be helpful. There you can get a ring expansion. Positive charge
Yeah.
will come here, alcohol will come at this position. Done?
Uh,
Right. Next question. Oxymercuration, demercuration. Pi bond when you attack Hg plus 2. Okay, you can see first HgOAc twice will exist as HgOAc plus and ACO minus. Pi bond will attack on Hg plus. So this is the mercurium bridge that is formed. And on the more substituted side, water will always attack, breaking this bond.
yeah.
And then this is hydrolysis step which is done. And H plus has been lost. Mercury containing compound will be present here. Up to this process, the first two steps are called oxymercuration. The next step, if you notice, is BH4 minus attacking on this position so that mercury can leave with the electrons. So we can get OAc will go away, mercury will get deposited, BH3 will come out, and H will get added here. Okay. So here there is no carbocation. So what are the important features? Bridge compound, no carbocation, no rearrangement, Markovnikov followed, mercury is reduced, and it is non-stereospecific. Steps are clear.
Yes.
Third, check out these examples. Instead of water, if at all I take ETOD, that will become OET. And it is not the deuterium which is adding, it is the H minus which is adding. So H minus will be added here. That is a product. Same way, water and Na8D4. So OH will come from here, D will come from here. So this is the product. Internally, if there is OH, that O itself will attack and you will get this as a product. Examples are clear?
Yes, sir.
Next is oxymercuration, demercuration. Reagent is B2H6THF and peroxide.
Yeah.
See, in this B2H6 in the presence of THF will be relieving one BH3 which will act like an electrophile. Pi bond will attack on it. Simultaneously, hydrogen will attack, make a back attack on the carbon, which makes it to go through four-membered cyclic transition state. Okay. Thereafter, it will give you BH2, which will again become a new electrophile. That electrophile will be connected with the next pi bond. Imagine doing it three times. So you will get this three alkyl group. That's why it is called trialkyl borane. And in trialkyl borane, peroxide in basic medium will have a new HOO minus, which is a nucleophile, which will attack on boron. And from there, once the attack has been done, R minus will go attack on this RO group. So we will get this as OR, and OH minus will relieve. Like that,
Yeah.
you do it three times. So you will get this as OR here. So this will become trialkoxyborane. And on that, OH minus is attacked back. So that's how you can get this as ROH. And you do it for all three times. So basically, you'll get 3 moles of ROH. Okay. Clear. So what did we notice? It is no carbocation, no rearrangement. Trialkyl boron is formed. It is following anti-Markovnikov rule and it is still stereospecific. Very important. Here, unlike the first two cases of hydrolysis, here when you do hydrolysis, you will notice that it is since still stereospecific. That means final H addition and OH will be on the same direction. Okay. And 3 moles of alcohols will be formed in the product.
Yeah.
Correct. So you can see pi bond is there, B2, D6 is there. So D will get added here and OH will get added here, but both should be syn to each other. Okay. And that you can
Yeah.
represent in a cyclic structure. You can see for this structure, OD and H, OD and H. See, both of them are on the same side.
Yes.
This
Yes.
is 50%, 50%. So product is enantiomeric mixture, but both will be 50-50 percentage. Okay.
Yeah.
Instead of peroxide, if at all I take acid like CH3COH, it will undergo reduction. So instead of making OH, now you'll get H. So H and H will get added. Done.
Yeah.
Next, addition of X2 and H2O. X2 in H2O is HX plus HOX. Okay. HOX will have, pi bond attacking on X, relieving OH minus. Here also bridge bond is formed. OH minus attacks on the more substituted side and you'll get this one. Clear? This is called halohydrin. Okay.
Yeah.
Addition is called halohydrin.
Yes, sir.
Right. Clear? And addition is
Yes.
always anti-stereo specific.
Huh.
Anti-stereo specific
Specific.
addition. Done. Right. Next, if at all I take lithium aluminum hydride after this, that halogen can be replaced with hydrogen, and that's how you can get alcohols. No rearrangement, no carbocation here. Okay.
Huh.
Similarly, at this position, if at all there is an allylic group here, SeO2 is there. So at allylic position, you'll get an alcohol. Okay.
Yeah.
And usually alcohol gets to a more substituted allylic group, allylic position. So this
Regulation.
is
Okay.
major, this is
Yeah.
minor. Done.
Yes.
Next, hydroxylation. Bayer's reagent. Bayer's reagent is cold dilute alkaline KMnO4. Okay. The
Yeah.
oxidation state of manganese here is +7, and here there is a syn addition happening. Okay. So this is a syn hydroxylation. Syn hydroxylation, right? So that syn hydroxylation will give us two OH groups here. Manganese will convert into this one, which eventually convert into a brown black precipitate, which is MnO2. Oxidation state is +4. In the mechanism, you need to remember that manganese forms a manganate ester, because of which there is a syn addition. Okay. It is used to
Yes.
detect the unsaturation of double bond and triple bond. So syn
Yeah.
addition, manganate and black brown precipitate. Oxidation state change. Okay. Oxidation state change
Yes.
from where? +7 to +4. Done.
Yeah.
Same reaction with osmium tetroxide, osmate ester will form, syn addition will happen. This is the product you will get. Oxidation state, where is it changing from beta? +8 to +6.
+6. Yes.
Peroxy acids, if you notice, first step is epoxidation. So on the pi bond, when peroxy acid is being added, O linkage will come. So this is syn addition. Okay.
Yeah.
And then hydration of OH minus and H plus is observed. Okay.
Yeah.
So that will always be anti-addition. Okay. And see, anti-addition can be done in both acidic medium or a basic medium. Okay.
Yes.
So you can see Ag2O in the presence of H2O or H plus also does the same work. This is also going to give us same anti-addition. First epoxidation, then hydrolysis. Okay.
Hmm.
With Bayer's reagent, both OH should be on the same side. You can see that you will get a racemic mixture with both OH are on the same side.
Same
With
shade.
peroxy acids, both OH should be opposite side. Done.
Okay. Yes.
Next. From alkyl halides, if you notice from alkyl halides, react with aqueous NaOH, usually favors SN2 mechanism. Okay.
Yeah.
If it is tertiary, it will favor
SN1.
SN1 mechanism. Whether it is an aqueous NaOH or simple hydrolysis, both will give SN1 mechanism.
Hmm.
With O2, RMGX, when you react with O2, it will become RO minus, and RO minus on hydrolysis will become alcohol. Done.
Yes.
With aldehydes, right? Grignard's reagent, when you attack on formaldehyde, you will get this adduct, which on hydrolysis will give you 1 degree alcohol. Okay.
Hmm.
And if you have CH3 MgBr on acetal, you will get 2 degree alcohol. CH3Br on acetone, you will get 3 degree alcohol. Okay.
Okay. Yes.
Right. So that's how you can get these products. So you'll get racemic mixture in all. Clear beta?
Yeah.
From acid derivatives, we require CH3 MgBr to go through 2 moles at least. First mole will convert into ketone. Second mole will convert into alcohol. Okay. Ester also same thing. First mole will convert into ketone. Second mole will convert into alcohol. Right.
Yeah.
Anhydride also same thing. First mole will convert into alcohol. The second one, the other molecule, the one which broken up will be present in the form of acids. Only with cyanides, remember, only with cyanides, when CH3 attacks, you will first get this form, C double bond N minus. But the second
Hmm.
mole attack is not possible because carbon does not have sufficient delta positive charge. Because
Okay.
nitrogen is donating, this is donating, this is donating. So all of
Yeah.
them are donating, तो इसके ऊपर positive charge नहीं रहेगा. So second mole will not attack. Therefore, hydrolysis need to be done from here only. So it will give you imines, which on further hydrolysis will give you ketones. Agreed? So you
Yes.
will
Yes.
never get alcohols. You will get only ketones here. Okay. So even if you
Ah.
take excess, you will only get ketones. Done.
Um, yeah. Yes. Sir.
Epoxides. CH3 minus will attack. O minus will form. O minus will take H plus, and this is the product you will get. Okay.
Yeah.
If you have an unsymmetrical epoxides, CH3 will attack on the least substituted side, favoring an SN2 mechanism. You'll get an O minus. O minus will take H plus and you'll get alcohols.
Hmm.
Okay. This was a JE question. Look out how this has been. I think it is there in your sheet also. CH3 will
Hmm.
attack here via SN2 mechanism. You'll get this as O minus. O minus internally attacks and removes Cl minus. So that is a product you will get. Done.
Yeah.
And once you get this epoxide, if you do hydrolysis, you will get OH and OH. So this is the final product.
Hmm.
The next reagent is Bovold blank reduction, where sodium and ethanol is being taken. Sodium and ethanol is an electron provider. So if you take aldehyde or a ketone, you will get a dot here and O minus. O minus will take H plus from ethanol.
Hmm.
Second electron will also go, gets minus charge, again takes H plus from ethanol. That's how you will get alcohol. Okay.
Yeah.
But in case of aromatic aldehydes, these dots will terminate with each other like this and end up getting pinacoles. The vicinal
Hmm.
diols with alkyl groups are called pinacoles. Clear?
Yeah. Okay. Yes, sir.
But the better method of preparing pinacoles is to take magnesium mercury amalgam with water. Magnesium mercury amalgam is much richer source of electrons. So that will give more number of electrons. So more radical forms will be existing. So they will all terminate with each other.
Yeah.
And hence O minus can take H plus, convert into this pinacole forms. Right?
Hmm.
So 2 moles of ketones will convert into this pinacole. Clear?
Yes. Yeah.
Next, preparation from amines. 1 degree amine, when you diazotization is been done, that means HNO2 reaction will lead to give an electrophile NO plus, giving a
Hmm.
product disonium chloride. And that when
Yeah.
you react with water, warm water, or simply because it is already in an aqueous solution, if it is an alkyl group, disonium salt is extremely unstable. It will form a carbocation going towards more stable carbocation and hence giving alcohols. Okay.
Yeah.
See the mechanism. From primary amines, you will get a disonium salt. N2 will easily go away. Carbocation will form. You will get a carbocation rearrangement.
Hmm.
Now, before rearrangement, what are all the products possible? Since water can directly attack, you get alcohol. Chlorine can attack, you will
Yeah.
get chloride. Water can act like a base also, creating alkene. Okay.
Yes.
And these alcohols, when you react with a carbocation, existing carbocation, can get ether formation also. And this
Yeah.
alcohol, on reacting with this carbocation, can give this ketone, right? So same things. The secondary will also react with aqueous chloride, right? And
Hmm.
alkene, it is the same thing. So I have not written two times. So you'll get the same alkene. Okay. The
Yeah.
major product will be the alcohol, which is after rearrangement. Okay. So in total, if the question is asked, what are the maximum possible products you can get? So you can get 1, 2, 3, 4, 5, 6, 7, 8. Done. These are all the possible products. Clear?
One second. Yes, 1 second.
Hmm.
Hmm.
These are the examples. If you have a primary amine here, you get a carbocation, you get this positive charge. This is a CPM carbocation. CPM is a very stable carbocation, but at the same time, it can show dancing resonance, or some
Yeah.
amount will also convert into an expanded carbon, expanded ring. So these three carbocations will give three different alcohols. So you can see this product, and this product. Percentage wise, if you notice, this is 48 percentage, this is 47 percentage, and this is 5 percentage. Okay.
Yeah.
Right. Next, all reduction reactions by lithium aluminum hydride. Lithium aluminum hydride is a very strong reducing agent. It provides
Yes.
H minus, highly reactive in water. Okay.
Yeah.
Now notice lithium aluminum hydride, when you react with aldehyde, correct, that will convert into alcohol. Please remember that this marked hydrogen is coming from water and this marked hydrogen is coming from lithium aluminum hydride.
Okay.
Okay. So that's how you will get an alcohol in aldehydes or ketones. Clear? Now
Yeah.
check this out. Even if you react with acid chloride, it will end up getting first aldehyde, then further reduction will give you alcohol. Esters will also get aldehyde, further reduction will give you alcohols. Anhydride will give you aldehyde, further reduction will give you alcohols. Acid will also give you aldehyde, further reduction will give you alcohols. Okay.
Yeah.
Cyanides, instead of giving alcohols, they will give you amines. So
Hmm.
cyanides, amides, nitroso, nitro, oximes, they all will end up giving amines.
Yeah.
This is all the reductions behavior of lithium. Next, if you directly react with water, you will only get H2. If you react with alcohol, you will get H2. If you react with a hydrogen which is sufficiently polarized, that will also give H2. If you react with alkyl halide, whether it is methyl 1 degree, 2 degree, lithium aluminum hydride will give you alkane. Okay.
Yeah.
Next, tert butyl chloride will give you alkene. Only alkene, no reaction. Isocyanide, you'll get secondary amines. Okay.
Yeah.
Clear?
Yes, sir.
So these are the reactions of lithium aluminum hydride. Next, sodium boron hydride. It is very strong reducing agent, just as lithium aluminum hydride. It will also provide H minus. It is stable in water and alcohol, unlike lithium aluminum hydride. Okay. Now here also
Yes.
you can see same reaction happens with alcohols and ketones and acid chloride. But esters, anhydrides, acids, cyanides, amides, no reaction. Okay. Nitroso, we will get amine. Oximes, you will get amine. But with nitro, no reaction. Okay. So please understand the difference. Water, nothing will happen. Alcohol, nothing will happen. Acetylene, nothing will happen. But if I take 1 degree, 2 degree, you know, here, no reaction. Sorry, not 2 degree. 1 second. Yeah, 2 degree and 3 degree should be here. 2 degree and 3 degree, you will get a reduction towards this side. Okay. 2 degree is common for lithium aluminum hydride and NaBH4. Okay.
Mm.
Alkene, no reaction. Isonitrile, no reaction. Done. Clear, beta?
Yeah.
This is, a shade you should have it in front of you to understand the differences between these two. Clear?
Yes.
Next. Lithium aluminum hydride is a powerful reducing agent, right, compared to that of SBH, right? C double bond is more polarized because of the lithium here. Boron hydride overlap is stronger compared to aluminum hydrogen overlap. That's why aluminum hydride will be breaking up more easily. Second thing, if you have an isolated double bond, both will not disturb. So that double bond will remain the same. Only the aldehyde or a ketone will get reduced. But you have uh, conjugated, conjugated carbonyl group. Then with lithium aluminum hydride or sodium boron hydride, both will give only reduction on this position. But if the same conjugated form is in a cyclic structure with
Yeah.
sodium boron hydride, you will see first 1,4 addition will take place. So H minus will get added here and H plus will get added here. That brings the enol,
Mm.
which will further convert into ketone, and thereafter it will give 1,2 addition. So this is the difference in lithium aluminum hydride and SBH. Okay.
Yeah.
Similarly, if you have a cinnamic system, that means if you have a cinnamaldehyde, lithium aluminum hydride will give you 1,2 and 1,4 addition. So first it will give you 1,4 addition and then it will give you 1,2 addition. Okay. But
Yeah.
sodium boron hydride will only give you 1,2 addition. Okay. So you could notice here lithium aluminum hydride does not make 1,4. Here SBH does not make 1,4 addition. Okay.
Yes.
Reactivity wise, you notice aldehydes are more reactive than ketones, acid chlorides, anhydrides, esters, amides, and acids. Okay. How many moles that has been reacted? Check out. 4 moles of aldehyde will require 1 mole of lithium aluminum hydride. 4 moles of ester, 2 moles. 4 moles of acid chloride, 2 moles. Amides, 1 mole. To get 2 moles of, 2 is to 1 mole. Acid 4 is to 3 mole. The last one is very important. For acids, how many moles of lithium aluminum hydride are consumed? Okay. Clear with these points?
Yes.
Next. B2H6 reduction. B2H6 is best used for acids and amides. Those are best for acids and amides. You can see best reagents for acids, best reagent for amides. Okay.
Yeah.
So here when you react with aldehydes, it will give you, but it's an extremely slow reaction. Esters also slow reaction. So usually these three are considered not much of product formation at all. Acid chloride also no reaction. You know, acids and amides both will make best reaction with a double bond HBO reaction. HBO reaction we are aware of it. Just now we learned. Okay.
Yeah.
Next is MPV reduction. MPV reduction, Mervin-Pondroff-Verlet reduction, where you take one ketone in the presence of an alcohol with aluminium salt, aluminium isopropoxy compound. So that will make the ketone to get reduced into alcohol and the alcohol to get oxidized to ketone. So if this is your first ketone and this is the product, that means on the forward direction there is reduction happening. That is when it is called MPV reduction. On the backward side, it is called Oppenhier's oxidation. Okay, so you can see if the reaction has to favor more in the forward direction, the ketone too must have lower boiling point than the product so that it can distill very easily. Okay, clear? So backward reaction is called Oppenhier's oxidation, forward is called MPV reduction. Any doubt there?
Okay. That's understood.
Backward is Oppenhier's oxidation. Okay, got it? Right, I'll give you a minute's time. Please go through the entire reduction sheet once
Yeah.
asked from me. Okay, so first is about the acidic reactions. Acidic reactions of alcohols. Got it? For
Yeah.
example, if I take alcohol, right, and I treat this with uh, sodium hydride, so I will be getting H2 and RO minus Na plus. Okay. Same way, if I treat with NaNH2, NaNH2 is also very strong base. You will get H2 plus RO minus, sorry, not H2, NH3 plus Na plus. Got it? Even if you react with only sodium, you will get this as H2 plus RO minus Na plus. Got it?
Yeah.
Next, uh, if you treat that with NaHCO3, clear? If you
Yeah.
treat this with OH minus, if you treat this with phenoxide ion, OH minus, in all these cases, no reaction. Done? In all these
Yes.
cases, you will not find any reaction happening. Clear, beta? Right. Second type of reaction is substitution reaction. Substitution reactions that you need to check. So that includes alcohols, right? Reacting with various compounds. This is all something which you have learned already. SOCl2, it is SNI mechanism to get this as RCl SO2 plus HCl. Here important point is both of them are gases. So this is best reaction to, you know, get alkyl halides. Okay. Next is
Mm.
SOCl2 in the presence of pyridine. That makes it SN2 reaction. So it will give you RCl plus SO2 plus pyridinium chloride. Okay. Plus Cl minus. Got it? This is called Darzin's reaction. Clear? Next,
Okay.
PCl3 you'll get 3 moles of alkyl halide plus H3PO3. PCl5 you will get 1 mole of alkyl halide plus POCl3 plus HCl. Got it? You can write the same thing as red phosphorus X2. It is going to give you Rx only plus H3PO3. Got it? This is the same thing. Okay. Clear, beta? Next.
Yeah.
If you have HX, if you have HX concentrated, clear, it will also give you Rx. But here, usually if it is 1 degree, 1 degree alkyl halide, SN2 mechanism. If you have 2 degree and 3 degree, it will be SN1 mechanism. Okay.
Yeah.
This is something which we need to understand. Clear? Third
Yes.
reaction is about Lucas test. Third is about Lucas test.
Okay.
Lucas test is 3 degree alcohol when you react with uh, HCl in the presence of anhydrous AlCl3. Correct? That will convert into alkyl halide, 3 degree alkyl halide. Okay. This will be
Yeah.
turbid forming immediately. This is an immediate turbid. Got it? Same way, if you have 2 degree and 1 degree, clear? So you can see this is 2 degree and 1 degree if you have it, right? So this will be, let's say 2 degree and this is 1 degree. So for 2 degree, turbid would form, in 5 to 10 minutes.
Yeah.
Clear? While here, no turbid, only at high temperature.
Yeah.
Only at high temperature. Got it?
Yeah.
The next reaction of alcohols is esterification. Esterification. Esterification is observed when you have an acid RCOOH plus alcohol ROH R dash OH in the presence of H plus. Correct?
Yeah.
That will give you ester RC double bond O R dash plus H2O. Now remember here H from this end and OH from this end is the one which is forming water. Okay. So remember acid side OH and alcohol side H. This is the one which you will come across. Clear? Now rate of reaction, rate of esterification depends upon the lowest alkyl groups here. So HCOOH will have the more rate compared to CH3COOH compared to this one compared to dirt, right? Similarly, CH3OH will have more rate compared to C2H5OH compared to propanol compared to tert butanol and so on. Done. This is the rate of esterification that you will identify.
Yeah.
Clear, beta?
Yeah.
Right. This reaction is usually equilibrium. That means it is backward favored. If you want to make the reaction only in the forward direction, then instead of taking acid, we can take acid chloride and then R dash OH, correct? In the
Yeah.
presence of pyridine. So that will make the reaction to convert into RC double bond O, R dash and pyridinium chloride, right? So this reaction will avoid going in the backward direction. Okay. So only in forward direction. You can make the similar reaction even with anhydride also. So C double bond OR plus R dash OH. Then you will call this as RC double bond OR dash plus RCOOH. This is the product you will get. Okay. Clear, beta?
Yeah.
Now, if you notice here, we can also add something. Sorry, here, let me finish this part here only. Here we can also add something that in case if you have already existing ester O R dash plus something like ethanol is being added with 1:8 ratio, correct? Then you can get this to form RC double bond O OET plus R dash OH. Okay, this is called trans esterification. Trans esterification. So basically, we are replacing one alcoholic group with the other. Okay. So I suppose all these questions are clear. Now, see mainly applications that are being asked from the esterification kind will be these. First, salicylic acid esterific cases are the most asked ones. This is called salicylic acid. Salicylic acid. Okay. Salicylic acid, when you react with methanol, so you will get an acid base reaction here. So you'll get this as OH, sorry, not acid base, I meant to say esterification. COOCH3 here, correct? This will be
Yeah.
COCH3 here. So, what are we getting in this case? This alcohol, this is called methyl salicylate. Methyl salicylate. Methyl salicylate is also known as oil of wintergreen.
Yeah.
Next, you can react this with CH3 C double bond O Cl. So that will create an ester form on the alcoholic side, keeping this acid the same way. This is called aspirin. Okay, clear.
Mm.
Next, if you have PHOH, then you will get OH with COOPH. This is called phenyl salicylate. Phenyl salicylate, also known as Salol. Remember the names. Directly names can be
Yeah.
asked.
Okay.
Okay, clear? Right.
Yeah.
Now, the other type of reaction could be like this. Suppose if you have an OH group and NH2 group, and I use CH3 C double bond O Cl of one equivalent. Where is the reaction most favorable? See, between alcohol and amines. Amines are the first group which can make amides, which is more stable one. So this is the product you will write first with one equivalent.
Yeah.
Okay, done. Right. So these
Yeah.
are the examples and important pointers that you need to know it from esterification. Okay.
Yeah.
Next, dehydration. Dehydration, we have learned this as a part of elimination already, correct? So if you
Mm.
have anything like OH here and you are using concentrated H plus, okay, and heat,
Mm.
that will lead to dehydration and it will go via E1 mechanism. Concentrated H plus, you can get it from concentrated H2SO4 or concentrated H3PO4. Got it? You
Yeah.
can do the same reaction with E1 mechanism with Al2O3, correct, and heat. Al2O3 and heat. It will give you same kind of product and E1. Got it? And
Yeah.
similarly, if at all I have other reactions like OH here with Al2O3 and heat with pyridine, then you will get the same product, but this time it is E2 driven, E2 mechanism. E2 with Shezef as major product. Okay.
Yeah.
And if you use THO2 and heat, then you will get E2, but this time Hoffman as major product. Clear?
Mm.
For this, the other reagents, in a similar case, the other reagents include SOCl2 and heat, KHSO4 and heat, POCl3 and heat. All will give you same type of reaction. Done?
Yeah.
So you can go through the reagents thoroughly, check out in dehydration what are the reagents which are being utilized. Done? The next set of reaction of alcohols is about oxidation reactions. Oxidation reactions of alcohols. Okay. When it comes to oxidation, you need to check out whether it is primary alcohol or not, or primary, secondary, or tertiary or not. If it is primary alcohol oxidation reactions, that will give you uh, first aldehydes. Okay, first you'll get aldehydes, and aldehydes will get further oxidized to convert into acids. Then this is the complete oxidation which you will get. Got it? Now, whenever we make the oxidation of aldehydes, you usually end up getting acids. But when you have secondary alcohol, which is 2 degree, and you are making an oxidation here, correct? And oxidation here, so that will give you ketones
Yeah.
first. And that ketones, if you try to further oxidize, no reaction is usually observed. If you have tertiary alcohol, 3 degree alcohol, if I make an oxidation from here to here, correct? Here itself there is no reaction, correct? There is one more case where is a reaction on tertiary alcohols, right? Oxidation, but this is not oxidation, this is dehydration. That is done by copper and heat. So copper and heat will give you dehydration. Clear, beta?
Yes.
So now if you notice first of a kind, where this is first kind, clear? And this
Yeah.
is overall reaction from here to here. From here, sorry, till here. So that means it is not stopping at aldehydes. This is second of a kind. Okay.
Yeah.
Then this is third of a kind reaction. This is fourth of a kind reaction. Correct. Fourth of a kind is already given, so we don't have to worry about it. So what are the reagents? If you notice the reagents here, for first of a kind, the reagents that are used where it will only end up at aldehydes, that includes PCC, PDC, copper and heat. These are going to be stopping only at aldehydes. Okay,
Mm.
clear?
Yeah.
And third also it is the same thing. Sorry, second of a kind. If you notice, second of a kind will be KMNO4. You can see this is KMNO4 in acid or KMNO4 in basic medium, or K2Cr2O7 in acidic medium, or CrO3 CrO3 in acidic medium, correct, which is called as Jones reagent. It's called as Jones reagent. Okay, these are
Mm.
the reagents which will convert them into acids. Next, third of a kind, if you notice, we are trying to make the 2 degree alcohols to ketones, so all of them. Okay, 1 plus 2,
Mm.
1 plus 2 will make it all of them into ketones. Done.
Yeah.
So these are the reagents for oxidation that you need to remember. Got it? So each of them are being strong oxidizing and weak oxidizing. Okay. You might also
Yeah.
be asked about terms like Collins and Saritz reagent. So you can add that here. Collins reagent or Saritz reagent. Okay. Their work is the
Yeah.
same. You may not have to know the structure, but they do the exact same work. Got it?
Yeah.
Now, in all of these cases, okay, in manganese, in reduction case, sorry, oxidation change. When it comes to oxidation change cases here, what you will notice, MnO4 in H plus, right? It is changing from +7 and it will go all the way up to +2. MnO4
Mm.
in basic medium from +7, MnO4 minus. It will change
Yeah.
to MnO2, which is +4.
Mm.
Cr2O7 2 minus or CrO3. Both of them will have +6 oxidation state. That will convert into Cr +3. Got it?
Yes.
Okay. Right. So these are the oxidation changes which will happen between these ions. Got it?
Yeah.
Right. Just a minute. Another thing we can add here is, especially for 1 degree, correct?
Yeah.
Here, if you have 1 degree to get these cases, you can also have concentrated HNO3.
Yeah.
Okay. And the other product is if you have an alcohol, 1 degree alcohol with X2 and NaOH, right? Clear? X2
Yes.
and NaOH, this can convert into uh, aldehydes. And if you have secondary with X2 and NaOH, it can convert into ketones first. As a further reaction can happen and that will go to iodoform. That's a second story. That's a different story. But here, first keto formation is observed. Okay. So even with
Yeah.
X2 and heat, you will have a similar type of reaction. Clear, beta? Right.
Yeah.
Now, notice what is the order of pH of the solution. Correct? This pH will define their oxidizing nature as well. Understood? So if you
Yes.
notice Jones reagent, so Jones reagent will have very lower pH, then comes to PCC, then comes to PDC, and then comes to Collins, okay, or
Yeah.
Sarets. Clear?
Yes.
In fact, if you compare the acidic form, these two are mostly acidic. These two are
Yeah.
mostly acidic. PDC is almost neutral form, while Collins is basic. Okay, this is typically how that has been asked.
Yeah.
Clear? And whenever you have a strong oxidation state, you will notice that they can also disturb double bond. So double bond can also be broken, except for Jones reagent, it will not happen. So let me show you with an example. Okay. For instance, if at all I have a compound like this, I have a methyl here, and then I have an alcohol here with OH group and another alcohol OH here, correct? One OH on this position. Then I have a double bond group here like this with another OH here. Got it? Okay.
Yeah.
And let's say one more position where you have an OH group here like this. Done.
Yes.
Now for this compound, let us see what are all the reactions that is going to happen with different cases. Copper and heat. First, let us talk about copper and heat. What will happen? Okay. So if you take copper and heat, wherever there is a primary form, you convert that into aldehyde. Secondary form, you convert into ketone. So like this way, H. And tertiary, you convert into alkene. Okay. Here also you convert into aldehyde. Then that's it. This is the product that is formed. Done. Right.
Yeah.
Just a second. This is when you have copper and heat. Okay. Now, if at all I react this with only PCC, PCC, everything would be same here, right? There is hardly much difference. I mean, let me copy from here only. So for PCC, you will notice almost everything is same, except that on a triple bond position, nothing will happen. I mean, on the 3-degree alcohol, nothing will happen. That will remain the same, correct? This is PCC or PDC. Clear, beta? Hmm. And when it comes to Jones reagent, okay, if I take the same reactant here and make it reaction with the Jones reagent. So in case if you have reaction with CrO3 in the presence of H2SO4 dilute, okay. Now this is called Jones reagent. In the presence of Jones reagent, now secondary will become ketone, primary will become acid. So this will become acid. Nothing will happen to tertiary. Double bond is not going to get disturbed, and this will and allylic position and benzylic position will still remain aldehyde. Okay. While if the same reaction is being done with KMNO4, KMNO4 in acidic medium and heat, let's say this is what has been given. So in that case, now you will see here ketone is formed, and here acid is formed. At this position also acid will form, but more importantly double bond will break and this will become acid. And after breaking that, you will get this as oxalic acid, COOH and COOH. Alright, this is what will happen. This is with KMnO4. So remember, with KMnO4 the double bond cannot hold strong. Okay. Lastly, if at all I have only MnO2 and heat. MnO2 and heat is specifically for allylic and benzylic oxidation. So only allylic and benzylic. This is benzylic and this is allylic. That's it. Allylic and benzylic oxidation. So this is the product that you will notice. Okay. So quickly go through these products. Check it out, beta. I'll give you a minute's time. Uh, Diols and triols. Okay. So
Yeah.
the glycol which we have structure like this. This is glycol, then glycerol structure like this. These two are other alcoholic forms. This is
Yeah.
glycol and glycerol. Got it? Most importantly, reactions are asked here. Suppose if you have glycol, right, and you are making reactions with PCl5, logic is the same how we did for alcohols. This is what you will get, POCl3 and HCl. Same way,
Yeah.
if you react with SOCl2, you will get OH, Cl and Cl with SO2 plus HCl. Okay. Now the interesting reaction is with this one, HI. With HI, first two iodides will come. Hmm? And then two iodides are highly unstable on a vicinal position, weak diiodides.
Yeah.
They are unstable. So it will convert into giving it alkene. If this alkene is further reacted with HI, then you will get alkyl iodide. So in a way, you can notice that total of 3 moles of HI were used here. Got it?
Yeah.
3 moles of HI were used. Next, if you take anhydrous ZnCl2, if you react with anhydrous ZnCl2, okay, uh, sorry, I meant to say concentrated H2SO4, correct? Concentrated H2SO4 will convert that into dehydrated part, which is dioxane. This is called dioxane. Okay. And
Yeah.
similarly, if at all I react this with concentrated H3PO4, it will get polymerized form. So that means
Yeah.
OH and oxygen connected here, and then we'll have OH here like this. This is the form which you will have. Got it?
Yes.
And usually, if you have these alcohols and treat this with anhydrous ZnCl2, right? And heating on this part, clear? So this
Yeah.
will convert into an aldehyde form. This will convert into an aldehyde form, right? The same logic can be applied for glycerol also. Only one important example that you know with glycerol is this one, where you will have OH, OH, and OH. If at all I treat that with HI first, X moles of HI, which is excess. So we need to figure out how much amount of X moles are required.
Yeah.
So first 3 moles are required to get 3 iodides. Okay.
Hmm.
And next, because this is an unstable form, minus uh, you will get iodine out, so you'll get a double bond. And on this double bond, if at all I use HI again, I will be getting this as iodide here and iodide here. Okay. And these iodides will be again unstable form, so you'll get a double bond here. And that on reacting with one more HI, you will get iodide at the center. So that is a product. Clear? So total number of moles, how many? 3 moles here, and then 4 moles and 5 moles. So total how many moles? X is equal to 5. So 5 moles have been used here. Done.
Yeah.
This is the product formation. Any doubt?
No, sir, understood.
Next one is pinacol, pinacolone, pinacolone rearrangement. This one is the rearrangement which you will notice. All right. So basically, if you have anything like OH and OH here with more substituted groups like this, and this in the presence of H plus or any Lewis acid, BF3 or TSCl or SOCl2, H3PO4. So we can take any of that, correct? So here basically I can use this as TSCl, I can use SOCl2, I can use POCl3, I can use BF3, clear?
Yeah.
AlCl3. So any of these can be used. That will help in first removing out one OH group, clear? And
Yeah.
there you can get a carbocation. And from there, a methyl shift can take place, and then we can get a double bond O here. Okay, this is after
Yeah.
1,2 methyl shift. Usually, what to shift is already given, but in case if it is not given, just check out migrating aptitude. Migrating aptitude wise, if you compare, then hydrogen is more than phenyl with electron donating groups and only phenyl, then phenyl with electron withdrawing group, and then comes 3 degree, then 2 degree, then 1 degree, ethyl and methyl. Okay, this is the migrating aptitude that you need to remember.
Yeah.
Clear, beta? Okay, so
Yes.
when it comes to pinacolone, there are 4 steps, correct? So first is getting protonated, or that is trying to become good living group. Okay,
Yeah.
second one is carbocation formation, then migration. So this migrating aptitude is only between the intermolecular within the molecule, so it is intramolecular rearrangement. Okay,
Hmm.
so these
Yeah.
words will be used: intramolecular
Rearrangement.
rearrangement only.
Yeah.
Rearrangement from external source, there is no rearrangement happening. Got it?
Yes.
So which means there is no crossover products, no crossover products observed in this case. Clear?
Yeah.
And if migrating group has chirality, migrating group retains its chirality, retains its chirality.
Hmm.
So if it is R configured, it will remain R configured. If it is S configured, it will remain S configured.
As
Okay,
configured.
clear?
Yeah.
Right. This is the one thing you need to understand once. Right. So this is about how the migrating aptitude works in this case.
Yeah.
Clear? Now, in most of the cases, so mainly you need to learn about cyclohexyl cases. So starting with, check this example. Suppose if you have something of this side like this with, you know, OH on the equatorial position and NH2 on the axial position. And here we have a tert-butane, so that there is no flipping of ring. Now this when you react with HNO2, this when you react with HNO2, now what would happen? See, in such cases, first you will make a disonium salt. This will become N2 plus, isn't it? This will become N2 plus. Clear? While
Yeah.
while this group is going, now notice that there is a hydrogen here, correct? When this group is
Yes.
leaving, simultaneously hydrate shift will take place, correct? So
Yeah.
that makes it, as the hydrate shift happens, you can see this 6-membered ring, double bond O, and tert butane will be present here. So 75 to 80% will be this product only.
Yeah.
Clear? Is this case
Yes.
understood? Now, let me take second case. In this case, in the similar way, let me take the second case also. Right. Second case is by chance if NH2 is here, that is in the equatorial position. Okay. In that case, now N2 would be N2 plus will be here. Is that clear? Now,
Yeah.
since N2 plus is here, this time when N2 plus is leaving, this bond will break and this carbon will attack here. The bond will shift onto this side. Got it? And
Yes.
because of which, now you will have a 5-membered ring instead of 6-membered ring. Now you'll have a 5-membered ring like this with tert butyl group here. And on this side, we will have CHO. Clear?
Yes.
Right. Similarly, let me take one more case here. What if now the OH is on the opposite side here like this? OH is on this side, correct? And NH2 is here like this, correct?
Yeah.
In such case also, I mean, here you will see it is around 90 percentage. In such case also, the option would be very, very similar here. So that means we'll have OH here, H here, and NH, N2 plus here. So same thing, the group will go from here, attack would happen from here. So you will get a same product here, this one, but the percentage will be higher. This will be higher percentage. This will give you more percentage of around 98 percentage will be this product. Then
Yeah.
I guess this part is understood.
Yes,
Yeah,
sir.
correct. Only these three cases might be something extra that you need to remember. Got it? And in the test of alcohols, can test is the most important one. Okay, where we'll take ammonium cerium nitrate, correct? So here 6 like this, correct?
Yeah.
So this is ammonium cerium nitrate. So if you have 1 degree alcohol, correct, with ammonium cerium nitrate, clear?
Yeah.
So it will start converting into alcohol plus color change will happen. Got it?
Yeah.
So what does it change into? Okay, it will start converting into red color, correct? And then after some time it will become colorless. Okay. So
Yes.
2 degree alcohols also in the presence of can test, I mean in the presence of can, it will become ketonic form. That will also start becoming red color and it will also become colorless over the time. 3 degree alcohols also will make a complex. It does not form a product, but it will make a complex and that is also red color, but this does not fades away. So can test is given by all 1 degree, 2 degree, 3 degree. All of them will give you can test. Okay.
Yeah.
But in 3 degree, the color will stay. Clear, beta?
Yes.
Right. Now, second thing is about bromine water. So if you have a primary alcohol, if you react with Br2H2O, this bromine water is brown color. Clear? So that will convert
Yeah.
into an aldehyde. So that will become colorless. Got it?
Yes, sir.
So that's it. These two are the main tests that you need to learn it from alcohols, beta. Okay.
Hmm.
So if you ask me as a synopsis, this is how much you need to know it from the alcohols topic.